Somewhere in the universe, a black hole exists so massive that scientists can't even agree on how heavy it actually is. Not roughly, not approximately. One team's estimate, 66 billion suns. Another team's estimate, 40.7 billion. Both published, both peer-reviewed, both about the exact same object. In the next few minutes, I'll show you why both of those numbers matter and why the real story of TON 618 might be more disturbing than its size ever was. Its name is TON 618, and what we can't prove about it, that's the part that should keep you here. For over a decade, the most powerful object in the known universe sat filed away as nothing at all. 1957, Mexico, a routine night at the telescope. An astronomer logs a faint blue star, object number 618, nothing special. One entry among thousands. He moves on. For over a decade, nobody looks twice at it again. Here's the problem, it was never a star. Back then, the word quasar didn't even exist yet. There was no category for what they'd actually found. No name for something that could outshine an entire galaxy from a single point of light. So it just sat there, misfiled, ignored, hiding in plain sight inside a catalog for over 10 years. Until someone looked closer and the light broke every rule they had. In the 1970s, better instruments finally caught what the light was really doing. It wasn't shining like a star, it was stretched, redshifted, by a distance so extreme it barely made sense on paper. This wasn't a nearby star at all, it was the blazing heart of a galaxy, over 10 billion light years away, so far that its light left home before our own sun had even finished forming. They weren't looking at a star, they were looking straight into the past. A supermassive black hole, feeding at the center of a young galaxy, so bright it had been mistaken for a single, ordinary point of starlight for over a decade. That object kept its catalog number. TON 618, a single point of light was outshining an entire galaxy, and for years, nobody could explain how. Stars don't do this. Even the brightest ones in a galaxy are drowned out by the combined light of billions of others around them. But this point of light wasn't competing with its galaxy, it was burying it. So astronomers went looking for the mechanism. What could possibly generate that much energy from a region small enough to look like a single star, from 10 billion light years away? The answer they found was almost as unsettling as the question. At the center of that galaxy sat a supermassive black hole, pulling in gas and dust from everything around it. But here's the thing. That material doesn't just fall straight in, it spirals, forming a disk that heats through friction to tens of thousands of degrees, radiating across the entire electromagnetic spectrum. Radio waves, visible light, lethal X-rays, and some of that material, it never makes it in at all. Twisted magnetic fields grab it and launch it back out. Two colossal jets blasting from the black hole's poles at nearly the speed of light. Jets that stretch for millions of light years, longer than the galaxy producing them. That's the mechanism, a quasar. Case closed? Not quite. Because this answer immediately creates a bigger question. If quasars can burn this bright, why doesn't every black hole become one? Here's the twist. It's not about the black hole, it's about what's falling into it. Starve a black hole of gas and the light show stops. Completely, instantly. Even if the monster underneath is exactly the same size as TON 618, which means somewhere out there right now, black holes just as massive as this one could be sitting completely dark, completely invisible, simply because nothing nearby happens to be feeding them. Sit with that for a second. Then let's get back to the one we actually caught in the act. Once astronomers confirmed what TON 618 really was, they went back and asked the obvious next question. How bright? How big? The numbers didn't disappoint. TON 618 turned out to be one of the most luminous objects ever found, radiating with the power of over 100 trillion suns. Swap it in for the center of the Milky Way, and it wouldn't just be visible in daylight, it would outshine the full moon by a factor of over 20. Every constellation you've ever learned to recognize, gone, washed out. And the black hole behind all of it is large enough that our entire solar system, every planet, Mercury to Pluto, could be dropped inside its event horizon, with room left over. Don't believe it? NASA's own Goddard Space Flight Center built an animation comparing the shadows cast by the universe's biggest known black holes, side by side, at true scale. Sagittarius, a star, the giant at the center of our own galaxy, barely registers. Even the black hole in M87, the first one ever directly photographed, famous worldwide, looks small next to what comes at the very end of that comparison. Ton 618's shadow is so large that a beam of light moving at full speed would take weeks just to cross from one side of it to the other. Weeks for light to cross a shadow. So that's the size. Mystery solved, right? Wrong, because the mass is where this investigation falls apart all over again. The single most massive object ever measured, and two separate teams of scientists can't agree on its weight by 30 billion suns. In 2004, astronomer Ohad Shemer and his team measured Ton 618 using the width of a specific spectral line in its light called hydrogen beta. Based on how that line was stretched and broadened, they calculated a mass of roughly 66 billion suns. For years, that number became the headline, the record, the one every documentary, every article, every biggest black hole list repeated without question. Then, in 2019, a team led by astronomer Jianguo Ge revisited the measurement with improved methods. Their result, roughly 40.7 billion suns, almost 40% lower. Two credible, published, peer-reviewed measurements of the exact same object, off from each other by an amount larger than the entire mass of some other supermassive black holes combined. Here's why that gap actually matters, and isn't just measurement noise. The disagreement comes down to which spectral line you trust as your ruler and how you model the motion of gas swirling that close to a black hole's edge. Different assumptions, different physics, different answers for the single most extreme object we've ever tried to measure. If we can't agree on the mass of the biggest thing we've ever found, what does that say about the smaller ones we're far more confident about? And even that 40% gap isn't the strangest part, because Ton 618 doesn't even hold its title uncontested. A black hole at the center of the Phoenix cluster, cataloged as Phoenix a star, has occasionally been floated as potentially larger still. But its mass estimates swing even more wildly than Ton 618's, measured through indirect methods that stay poorly constrained. Nobody currently trusts that number enough to call it a confirmed record breaker, which means the biggest black hole in the universe, a title repeated in countless videos, articles, and trivia lists, doesn't actually have a settled owner. It has a leading candidate, wrapped in a 40% margin of error, being chased by a runner-up we can barely measure at all. Because whichever number turns out to be closer to true, both of them create the same problem. There wasn't enough time in the universe for this thing to exist. And it exists anyway. Supermassive black holes are thought to start small, collapsed remnants of the very first generation of stars, or the direct collapse of massive primordial gas clouds. From there, the standard picture is slow, swallowing gas, merging with other black holes, growing patiently over billions of years. Ton 618 breaks that timeline. Its light left its source when the universe was less than a quarter of its current age, meaning whatever process built a black hole tens of billions of times heavier than our sun, it had to happen shockingly fast by cosmic standards. Today, astronomers are split. One camp believes these giants skipped the slow start entirely, forming from the direct collapse of enormous gas clouds and beginning life already massive. Another argues they feed in violent, repeated bursts that briefly exceed the theoretical brightness limit for how fast matter can fall into a black hole, gorging faster than the textbook physics allows. If the second group is right, then everything we've assumed about how fast the universe's earliest giants could grow begins to collapse. Neither camp has won yet. Both require conditions in the early universe more extreme than most models originally assumed. To put the pace in perspective, even under generous assumptions, a black hole growing by swallowing gas and merging with others needs enormous stretches of cosmic time to reach tens of billions of solar masses. Ton 618 didn't have that time. The universe simply wasn't old enough yet. Something about its early environment let it skip steps that, by the textbook, shouldn't be skippable. And that raises an uncomfortable follow-up question. If we can't even be sure how Ton 618 got this big, how confident should we be that we've found all the ones that did? A black hole as massive as Ton 618 could be sitting far closer to us than 10 billion light years, and we would have no way of knowing. Remember the fuel problem from earlier. A quasar isn't the black hole itself. It's the black hole while it's actively feeding. Gas spiraling in, friction, light. The moment the fuel runs out, the light show ends completely. The black hole doesn't shrink, doesn't weaken, doesn't become less massive. It just goes dark. Astronomers have a name for this state: quiescent, dormant, and here's the part that should actually unsettle you. Almost everything we know about supermassive black holes comes from finding the ones that happen to be feeding right now. Bright ones, loud ones, quasars like Ton 618. The quiet ones don't announce themselves. They don't send out jets. They don't heat a disk to tens of thousands of degrees. From the outside, a dormant black hole tens of billions of times the mass of the sun would look like nothing at all. A patch of space slightly too good at bending the light behind it. Easy to miss unless you happen to be looking in exactly the right place, with exactly the right instrument, at exactly the right moment. We didn't find Ton 618 because we went looking for it specifically. We found it because it happened to be screaming loud enough for a 1957 telescope to notice, mistaken for a star. Which raises the actual question this chapter is built on. How many objects just as massive, just as extreme, are sitting in complete silence right now, not 10 billion light years away, but far closer, simply because nothing is currently falling into them? We don't know. We can't know, not with our current methods. We can only find the ones that are loud. That's not a comforting thought. It's not supposed to be. It's the actual, honest shape of the problem. The universe's biggest objects are hiding not because they're far away, but because silence is the natural state of a black hole, and noise is the exception. In recent years, the James Webb Space Telescope has been finding more of them. Other black holes, sitting even earlier in cosmic history than Ton 618, that are, by every existing model, simply too heavy for their age. Objects that shouldn't have had time to grow that large, showing up again and again the deeper JWST looks. Ton 618 wasn't a one-time fluke. It was the first clear sign of a pattern we're only now starting to take seriously. If JWST keeps finding more of them, Ton 618 may stop being the exception and start becoming the rule. Which means the real question was never just, how big is this one object? It's whether our entire timeline for how the earliest giants of the universe were built is quietly, systematically wrong. We still don't fully agree on how heavy Ton 618 actually is. Two respected teams, two rigorous methods, and a gap of almost 30 billion suns between their answers. We're still not sure exactly how it grew large enough to outshine its entire galaxy while the universe was still in its infancy. And the more places we look, the more of these impossibly early giants we keep finding. Maybe the real mystery here was never Ton 618's size. Maybe it's how much of our picture of the early universe has been built on a number we're still, right now, actively arguing about. Somewhere out there, 10 billion years in the past, light is still leaving the edge of that black hole, carrying an answer we haven't fully worked out yet. Every time we build a better telescope, the universe doesn't become simpler. It becomes stranger. Maybe discovery was never really about finding answers. Maybe it's about discovering how many of our answers were wrong. This is NOVADREAD, and the further we look, the less settled the universe